introduction. And today, I'm delighted to talk about my research group working on sort of next generation wireless networking, most specifically in sensing and security and communication in the sub-terahertz and terahertz regime. We'll see some design components and some experimental results today that might be interesting to you. So maybe I'll start by briefly introducing my lab. So my lab is called SWAN, Smart Wireless Agile Network Lab at Princeton. On the high level, we are targeting 3 research areas. We are working on wireless networks in the millimeter wave regime. So anything from 28 gigahertz below 100 gigahertz, we call it millimeter wave. And we're particularly interested in the sort of MAC layer aspects of this millimeter wave networks. We are also working on terahertz common sensing. You'll hear a lot about this topic in today's talk. And we're also working on cross-cutting topics, including making the wireless system more intelligent, and also considering the security aspects of the wireless systems in 6G. Okay, so now why we are interested so much in this high frequency vision? Well, this is sort of obvious to most of you. Most of the emerging applications like virtual reality, augmented reality, connected vehicles, connected drones, they all require multi-gigabit per second communication links and millisecond scale latency. Unfortunately, today's wireless network cannot support such applications. So we need something better. We need to look into what options we have to sort of get this very strict sort of requirement into the network. We envision that moving to higher frequencies would be a key component. If you look at this sort of spectrum here, can you see my cursor, by the way? Yeah, so if you look into this spectrum, here's where we are currently operating. Today's Wi-Fi spectrum is below 6 gigahertz. Millimeter wave is, as I said, from 28 gigahertz all the way to 100 gigahertz. So for example, in the 6 gigahertz band alone, we have 14 gigahertz of available spectrum. This gigahertz scale bandwidth can translate to gigabit per second data rate in theory, but there are a lot of challenges and we will see a lot of them today. Moving up even further above 100 gigahertz, we have a sort of large swath of available spectrum that is unused. And there's huge chance, there's huge opportunity here for doing a lot of full communication and sensing that we just simply cannot do in lower frequencies. Okay, but why we cannot do it today? What are the fundamental challenges? I'll divide them maybe in 3 main categories. One is the physical layer challenges. As we move to higher frequencies, one limitation that we'll see is that signal will attenuate faster as they propagate in the air. Right. So if you want to reach the same range as like your communication links today you need to do something different. You need to focus your beams into a specific direction. You need to, and instead of broadcasting your energy everywhere, you need to kind of form these laser-shaped beams and kind of very focus your beam into the direction of your target receiver. Creating these directional beams and being able to control them electronically and in a fast manner is challenge in this high frequency. So that's challenge number 1. Now, challenge number 2 is on the medium axis. So now that we are sort of migrating from an omnidirectional wireless mode to a directional wireless mode, we cannot use or scale all the coordination techniques that we apply today. So links need to be point-to-point, directional. If users move, we need to adjust the beam. So everything needs to be different in the medium axis right now. If we fail to do so, if we, let's say, take too much time in finding the right beam direction, then we will not achieve the ultra latency because it takes so much time to do the training. And then, of course, your data transmission would be directional and fast in terahertz regime, but we already wasted so much time. So overall, we're not going to get so much gain by moving up to a spectrum. Now, and another challenge is on the architecture side. So we have because of the high penetration loss, we have the blockage issue. So signals can get blocked quite easily. One solution is, of course, to deploy more access points so that you can have a dense infrastructure that deals with blockage, but that's not going to be cost efficient. What we are interested in is designing new scalable architectures like smart surfaces that are low cost, easy to scale, and that can be deployed to help with the blockage issue. You'll see a few examples of this today. Finally, power consumption is one of the biggest challenges. So as we move to higher frequencies, generating these high frequency signals would be more power demanding on the circuit side. And also you need to deal with directionality. So you need multiple antennas. It's going to be a more complicated system that would also drain more sort of power from your battery powered device. So without solving this issue, without having a practical solution for limiting the power consumption of these high frequency circuits, there is no realistic pathway for these high frequency signals to get into our future mobile phones. Okay, so in this talk, I'll talk about all of these three problems. I'll give you sort of short solutions and I'll provide references. If you're interested in learning more, of course, go and read the paper. But the purpose of this talk is just to give you an overview of the type of problems that we have and the type of research solution that we are seeking. On the physical layer, I'll talk about a novel approach for terahertz beam steering, so generating these beams directionally and steering them in a fast manner. On the MAC layer, I'll talk about how we can do this coordination in single shot, in nanosecond scale, so everything will be in real time. To do so, we need to also track the mobility of the device, because as the device moves, you need to change, of course, your coordination, change your beam direction. So for this to be successful, you need to have some understanding of the device location and also the environment around. On the architecture side, I will introduce sort of a most power efficient architecture known as backscattering. I'll tell you how we can scale this up to terahertz for the first time. And I'll talk a little bit about reconfigurable smart surfaces, mostly in the context of security, because as you can see on the slides, one of the topics is the new paradigms for wireless security in the context of sub-Terahertz regime. Okay, let's get started with the first one. So for beam steering solutions, as I mentioned, we have directional. We need to create directional beams to overcome path loss, right? And as we move to higher frequencies, this directionality needs to increase, and that means the beams needs to get narrower and narrower. Typically, this is done by putting a large number of antennas in the form of phased array. But it's very challenging to develop a larger scale phased array above 100 gigahertz for various sort of reasons like heat dissipation, efficiency, so on and so forth. So what we thought about is, can we find an alternative solution? So instead of doing this phase shifting based beam generation and beam steering, can we find an alternative way of doing this more efficient and in a scalable manner? Then we realize, okay, what is the thing that we have a lot in higher frequencies? We have a lot of bandwidth, right? That's the reason why we are moving to higher frequencies anyway. So can we come up with a solution that this frequency is used as a commodity to enable beam steering? So the idea is, can we do frequency controlled beam steering? So let me introduce a very unique sort of antenna architecture that's very different from phased array. It's called Leaky wave antenna. So Leaky wave antenna can be realized with just a waveguide where two pieces of metal are put in parallel and you have an open slit in one side, as you can see here. We can also sort of fabricate this with CMOS, as you can see here. This is from one of my colleagues here, Kaushik and Gupta's group. They fabricated this on this CMOS chip. So the key or cool thing about this antenna is, if you inject a signal inside the waveguide, let's see this sort of parallel plate waveguide as an example. The wave will travel through the waveguide, and when it reaches the open slit here, it will leak out. That's why it's called leaky antenna. But more interestingly, it will leak out at a particular angle, and the direction of which is correlated with the frequency of the input signal. How do we get there? So it's kind of a Maxwell equation, simple physics. You write the full equation inside the waveguide in free space. You know, in the open slit, you have to satisfy the boundary conditions. You can write that, and with simple derivation, we can find the angle of emission from the waveguide as a function of frequency. So this C naught here is the speed of light, and B is the plate separation between these two waveguide like metal plates. Okay, so this is cool. This is interesting, right? So we have a device right now that, depending on the frequency that you inject, you'll get one directional radiation at a particular angle, right? So let's see the simulated result for this leaky wave antenna. You can see here that if I change the frequency from 100 gigahertz to 800 gigahertz, the emission angle, or that phi sub f, would vary from 10 to 80 degrees. So higher frequencies would emit at lower angle and vice versa. So this is kind of fairly easy. If I tune my input frequency, I can enable frequency control beam speed. It's a single antenna, so it's a single aperture. You can easily think about scaling this to an array of leaky antennas, or when you put one single waveguide and like have multiple open slits on the top plate. So there's a lot of things to play with, but on a very simple high level, this is the frequency control beam speed. It's also a very cheap and a small device in terms of design. So you can easily think about putting this in your mobile phone, or like any sort of battery powered device that needs like a small light and cheap RF front end. So the key idea was, now we are doing tuning the input frequency, and that will give us the beam direction. We can also change the beam width of the radiated pattern by changing the bandwidth that we put into the waveguide, right? Very simple. So interestingly, this will open up sort of new field of research, and I will show this as a building block for the rest of the talk. But things that I won't talk about, and very interesting observation, is because of this non-linearity between the frequency and angle, the bandwidth of the radiation is also a nonlinear function of angle. Meaning that if you think about this leaky wave antenna as a transmitter, and you put multiple receivers just around this, not every one of them will receive the same amount of bandwidth. It really depends on the location relative to the transmitter, which is completely different from our today's like wireless transmitter and receiver. The other interesting observation is that when you're sending a modulated signal inside the waveguide, let's say you're using OFDM. So you have an OFDM modulated signal as an input to this waveguide. What happens on the output is different subcarriers will sort of diverge a little bit from the center angle. So if you look at your received power, not all subcarriers will be uniformly sort of powerful. So center frequency will be more powerful, then you see a drop as you deviate from that center frequency. That's called beam squeeze. So what will the impact of that on your reach error rate, on your constellation, everything around those lines is something very interesting, and we haven't started looking into that. Okay, but we will use this device as a building block for our MAC layer and for our architecture solution that happens, that I will talk about in the rest of the talk. Okay, let's just start with the MAC layer. So what is the challenge? So what I want to do is I want to establish a directional link between a transmitter and receiver. And I want to adapt my directional beam as soon as the receiver moves, like ideally without seeing any drop in the received power, right? Without seeing any degradation in the quality of the link. Now, how is done today? Of course, terahertz is not deployed yet, so there is no standardization, there's nothing, but we can look into lower frequencies like millimeter wave, where we have it done. So we have IEEE H.11 AD and AY, and the suggestion there is basically trial and error. So let's say this is like my transmitter. What it does is it goes through multiple rounds of transmissions from different beam directions, every time sending a beacon, or what is called a sector sweep frame. On the receive side, you're measuring the strength of this beacon and basically saying, okay, which one of these beam configuration was giving me the highest power? So I will choose that one. I will log to that one. So the receiver report this information back to the access point, right? So it's a very lengthy process and iterative. And the scale of that really depends on how many beams you have, right? So it's O of n being the number of beams. This is under the assumption that your receiver is omnidirectional. So if both of them are sort of directional, then it's going to be order of n squared. And imagine you have to repeat that every time there is a mobility or there's a blockage in the system, because those beams will no longer work for the communication. Now, if we scale the same solution to terahertz, what happens? The beams are now narrower, so n is larger, right? I cannot afford to have an omnidirectional receiver. So it should be directional to directional. And I am much more sensitive to mobility because, again, my beams are narrower. So if I move a little bit, I lose my connectivity. So I really need to adapt to mobility in a much finer time resolution. Okay, so this won't work. So what is an alternative solution? So in an ideal world, if I know the location and like the environment, the location of the receiver and the environment, this is an easy problem. Fortunately, millimeter wave and terahertz channels are sparse, meaning that because we have high reflection attenuation, there are only a few physical paths, line of sight, maybe first order reflections that can carry information. So if I, instead of localizing the whole environment or the receiver, if I figure out those paths, like at least the angle of them, and track them in real time, I'm good. I can instantly steer to that direction. I can instantly do blockage recovery because I know a reflection. So as soon as I see a drop, I can just use to my backup path, like move to my backup path. And I have to do this in real time. So if I have this information in real time, I can do mobility adaptation. I can even do interference management in the context of multi-user transmission, right? But okay, how do we get this information? Well, if we look into like literature for angle of arrival, angle of departure estimation, there are two categories of multi-shot approaches, multi-antenna approaches. Multi-shot approaches are, again, iterative solutions. So you send signals, we have different like unique IDs into different directions. You get feedback from the receiver and you localize the receiver. I mean, this won't work for the same reason that the IEEE standard 8.11ad AY sector sweep training won't work. It's high latency, it's relative, it scales with the number of directions. The second category is multi-antenna solutions, when you have one basically impinging signal, so you record the phase that you see across different antenna elements, and you try to extract angle of arrival by comparing the phase that you see across antenna elements. This will work, but it requires a large antenna arrays and your access to read the phase of each individual antenna element. So if you have n antennas, you need n RF chain, right, to read those. And that is costly, over-consuming, and not practical. So what we did instead is we proposed a single antenna path discovery protocol in terahertz wireless network. This is published in Nature Com and also ICM Mobicom. Okay, how does this work? So what we want is we want to identify this high rate physical path. That's the goal. Our idea is that let's transmit signals that have unique spectral signatures, rather than sending unique IDs, sending unique spectral signatures across different angles, all at once, like sending F1, F2, F3, F6 in these different directions, and then let the receiver measure its power spectrum and figure out, based on the frequency peak that it receives, figure out the direction or the angle of arrival in a very fast single shot manner. To do so, you can already guess we will use a leaky wave antenna. We already know how to deal with this. So instead of now sending one single frequency into the waveguide, we send a pulse. This pulse in time domain, of course, in frequency domain contains all frequencies, right? So you're injecting all frequencies all at once. And what happens is that these frequencies will emerge out at a slightly different angle, creating what we call a terahertz rainbow. And on the receive side, a portion of these waves, depending on the location of the receiver, will couple into the waveguide, will be received in the waveguide. For example, here the yellow waveform, you can see it's received. And by sort of processing this, you can now correlate the spectral properties that you're receiving at the receiver with the spatial properties of your receiver, meaning where it is located at. Okay, so it involves a one-shot transmission. So you send a pulse and you send it one time. So it's super fast, it's in the order of nanoseconds. The node architecture requires one antenna only, so it's low complexity. And it's also scalable with increasing number of users. So if I imagine I have multiple receivers all at different angles, they can all independently receive this waveform from the terahertz rainbow transmission, process it, and localize themselves with respect to the transmitter. Cool, okay. So I won't go to the details of how to model these properties or signatures at different angles, but on a very high level, I can give you a model on based on like your angle, what is the, not just particular frequency, but what is the shape of your at a particular angle. And that is unique to that leaky wave antenna and the characteristics of that. But with a known model, it's not a random model. So with a known model, you can write that down. I call it here G. So on the receive side, you see G of the line of sight angle at frequency F times the alpha, which is supposed to get the channel gain. So it's a complex number that gets the channel sort of amplitude and also phase. And basically at the receiver, you see the summation of all of these signatures impacted by the channel coming from different physical paths. So you have one line of sight and one line of sight, you see basically the superposition of the two. Now, you can form an optimization framework. You have a measured power spectrum and you have an expected power spectrum, right? Knowing this model. Then you can find which angles are giving me the minimum distance between the measured power spectrum and the model. Cool. So without going into details, let's see some sort of experimental results on this. So maybe before that, just a one-on-one comparison between our approach to Terahertz rainbow and a conventional beam training. In conventional beam training, you send a unique ID in each direction. Here, we are sending a spectral signature at each angle. In the sort of conventional approach, you're trying one beam at a time. Here, we are sending to all directions at once. The training time can take up to hundreds of microseconds. Here, the total overhead is about nanoseconds. So it's much faster and scalable than the traditional approach. Now, how did we test? So we have a terahertz pulse generator and an ultra-wideband detector. Here you can see it. This is the spectrum of the pulse in time domain and a spectrum of the pulse in frequency domain. You can see it goes from like 0 to 2 terahertz, but it's flat until like 400 gigahertz. It's a low power output, so that means that our range is limited, but nothing actually changed if you just kind of replace this with a higher, like a stronger source. Like your range scales, nothing on the spatial properties of your leaky wave antenna would change, you just get to higher ranges. This is our custom leaky wave antenna with a single slit. The spacing here is about 1 millimeter between the metal plates. So we did try this in different configurations, different distances between transmitter and receivers, different angles. And this is the summary of results. So for line of sight path, the average estimation error is about 1 degree. For non-line of sight path, which is weaker, of course, so closer to the noise floor, it's about 2 degrees of error for your angular estimation. How can we improve that? So there are several ways we can improve that. We can discuss this offline if you want, but like just to name a few, of course, improving the output power at the transmitter would help. You can think about methods when you basically find a coarse estimation first, and then you zoom in by sending like, instead of sending a pulse, sending a sort of narrow band frequency inside and kind of zoom in and try to further improve your accuracy. You can change your architecture, think about multi-slit architectures where you have multiple points of reference, and that can help you improve your accuracy. Okay, so how is this helpful in the context of beam adaptation? Remember, we wanted to say in a very fast manner, we can adapt the beam direction as soon as the user moves, right? Let's say I'm locking into one direction and my user starts moving. What I want to do is I want to be able to get the link back in nanosecond scale. What I will do is I send the terahertz rainbow, right? I'll estimate the path, and now I have an angle. That angle is not 100% correct. As you see, the average is about 1 degree in line of sight, and the average area is about 1 degree. So that means that I'm not 100% pointing to the receiver anymore. And that would mean that I'm seeing a SNR penalty. So we did some experiment and find out that the SNR penalty is about 1.2 dB in 90% of measurement instances. So that of course depends on how wide your beam is. Here, the beam width was about 3.5 degrees, so it's a super narrow beam. Of course, for wider beams, the error is, the penalty is much smaller. Interestingly, I mean, one of the things that I mentioned is depending on the angle, you see a different bandwidth, right? So if we are measuring this in this figure on the left, So the bandwidth that you see, depending on the non-line of sight angle, can change from sort of 2.5 to almost 0.5 and matches the model. That means that even, let's say your line of sight angle is the particular angle. Let's say your line of sight angle is like about 50 something, and your non-line of sight angle is about 30 something, right? So even though the non-line of sight angle is, non-line of sight path is weaker because it travels a longer path, it goes through a reflection loss, but because the bandwidth is larger, you can actually see a higher capacity and a higher data rate from a non-line of sight path, which is an interesting observation because non-line of sight paths are typically known to be much weaker than line of sight paths. But that might not be true anymore with this new node architecture. Okay, so we haven't talked about the rotation of the device, right? Let me skip this because there's a lot that we have to talk about. But the key idea is based on this one single transmission, you can also measure the amount of rotation or the orientation of receiver. This can be helpful for gesture recognition. Let's imagine the Leaky wave antenna is attached to your smartwatch and you wanna detect the hand gesture, right? As I'm talking, I'm moving my hands a lot. So that can be one application, for example, because you can, in a very fast manner, estimate the rotation. And we showed that this really works in practice with our experiments. Okay, so far I talked about using this Leaky wave antenna for mobility management. What we haven't talked about is potentially using this for blockage sensing, because if blockage happens, you need to find an alternative path or do something differently because your signal is no longer, your link is no longer valid. So what we tried doing here, and this is published in ACM Census, is depending on where your object is located, maybe I'll go back a slide, depending on where your object is located at, and it's like geometric features like its size, it will block certain frequencies. So if I send my rainbow again, and I look at the sort of measured power spectrum across few snapshots, right? I can say, okay, this is supposed to be, I'm supposed to see this spectrum, but a few of these frequencies, I see a dip, I see like lots of absorption in it. If I do some data processing on top and compare these snapshots across time, I can actually localize my blockage, my blocker here, even find out its mobility. So that's the key idea. You can model this based on, again, the spectral signatures that is being emitted at different angles. So each angle is seeing different frequency. So if the object, like intuitively, if the object is bigger, it's impacting more frequencies, right? If it's closer to the transmitter, to the Leaky wave antenna, it will impact more frequencies. So you can also localize the range of the object relative to the transmitter. So we did some experiments here again, and here what I'm doing is I'm moving an object from right edge, like outside of the field of view, all the way to the left edge. And every time I'm measuring my power spectrum, again, it's a one-time measurement, so it's super fast. And what I'm trying to do is I'm trying to localize my object, and see if there's an object or not, right, to begin with. So you can see that before actually reaching this right edge RE, I see my signal is like kind of saturated at a particular angle. But as soon as this starts kind of touching the field of view, I can start localizing my object, the center of my object. And when on the other side, it goes outside of the field of view again, my signal is back up. So I can see whether there is a blockage or not, but then also can localize the block. Okay, so all of this was with a single Leaky wave antenna, which was giving me a sort of fan-shaped beam, meaning that it's directional in azimuth angle, but it's omnidirectional in the elevation angle, right? So we implemented a 3D version of this by putting two perpendicular slits. So what we do is we have a signal, like a pulse in, we have a power splitter inside the waveguide, and half of the pulse goes to the horizontal slit, and half of it goes to the vertical slit. And this creates like sort of a two rainbow that are kind of directional in two different planes. Interestingly, the polarization of the waves would be different. So in vertical and horizontal polarization will be seen, so they will not interfere with each other. If they interpret the chain, that would add a lot of ambiguity to your sensing, to your localization. So now I have a receiver, it's dual polarized, and I measure my signal both in vertical and horizontal polarization. So I have two reference points, and I can localize my receiver with respect to this integrating. So that's the key idea. We also did ranging. So ranging is typically done through either sending a chirps or kind of typical radar processing, or by knowing the exact time of arrival, right? Both of them are costly in these higher frequencies. But we propose this based on the bandwidths of the signal that you receive. You can do non-coherent, meaning that you don't require phase or timing information, you just need amplitude. You can do non-coherent ranging for the first time. So if my, like again, putting it in a very simple way, if my receiver is farther from the leaky antenna, it will receive a narrower beam, right? If it's closer, it will receive a wider range of beam. So bandwidth increases as range decreases, right? Okay, cool. So this is also sort of accepted to ACM Mobicom. It's going to be presented this year in Sydney. Okay, cool. So far I talked about a novel sort of beam steering solution, and I use that building block to do real-time mobility estimation, blockage sensing, and coordination, like link establishment. What I want to talk about next is terahertz backscattering, which is the most power-efficient architecture known for terahertz. Okay, so just like one background information, at lower frequency, like at 28 gigahertz, like the development of this sort of circuitry has been slowed for mobile phones because of the high power consumption. So this will worsen at higher frequencies for sure. Why is it high power consuming? So the circuit for generating the signal and amplification is power consuming, and then we need large antenna arrays for directional beams, and that also increases the power consumption. What we're proposing here is sort of an architecture that is directional, it's ultra-wideband, but it consumes 0 to little power. So the key idea is, instead of generating and transmitting new terahertz signal, what we do is we piggyback the information on the impinging on the ambient terahertz signal. So you have an external powerful transmitter, all right, and your like mobile phone or like your power constrained device will impinge it will piggyback its data on top of this ambient signal that is being transmitted. This idea is known, and it's called backscattering, and it has been implemented in RFIDs and a few of other sort of power-constrained IoT architectures right now. But it's hard to scale it to higher frequencies. For one, you need to have directionality, and that's hard to do in like this backscattering architecture. And also all of the existing backscattering architecture are accepting a very narrow band signal. So like few megahertz of bandwidth, that's the best case scenario. So doing this in a multi-gigahertz bandwidth, which is essential to get high data rate for terahertz, is a key challenge. So the requirement number one is wide bandwidth, and the requirement number two is directional transmission and reception while drawing minimum power. This work is accepted and will be presented at NSDI. Okay, so to solve this problem, we designed a novel backscattering architecture, again using Leaky wave antennas. Our key observation is that this waveguide, this sort of angle frequency relationship is reciprocal, meaning that just like transmission, when you injected the signal in and it gives you a directional transmission at a particular angle, on the reception mode, if you are injecting or if you're like impinging all the frequencies at a particular angle, only one frequency will couple into the waveguide. So if you have a receiver or detector at the end, it will only receive one frequency. And that's the frequency that matches best. So the angle frequency relationship is the same. We did some measurements and confirmed that. We can see here that this sort of the red curves are in sort of different frequencies, but like or different angles, but one in transmission mode, one in reception. So the same colors are when you are just changing the transmission mode to reception. And you can see the pattern to a good extent actually overlap with each other. Okay, so how do we use this? Now imagine I have two slits. One of them is receiving a signal. So I have an external transmitter sending a signal with frequency F, with tone F, impinges on the waveguide. It couples in if it's at the right angle, right? It goes through the waveguide. I'll put some mirror, some sort of guide inside the waveguide to change the trajectory and kind of guide it toward the second slit. And then because it's the same frequency, I then change the frequency, right? It will leak out in the exact same direction. So it's a retro-directive link that you are establishing right now, and you consumed 0 power for that. There's no active component here, right? You consume 0 power, but you established a retro-directive link with an external transceiver here. Now, what I haven't talked about is how to embed your data, right? So this is an unmodulated signal. Your data is at the Leaky scatter. We call this architecture Leaky scatter. It's at the Leaky scatter. So how would you modulate your signal? And we are exploring a lot of options. Our first sort of prototype uses a millimeter size MEMS mirror inside the waveguide. These are very small mirrors that are controllable by basically putting a small voltage here, 5 volt. You apply a 5 volt and you can control based on the voltage that we applied from 0 to 5. You control the orientation of this mirror. I'll put it like here. You can see it here or here, right? Now, why is it important? Basically, what I'm doing here is I am doing amplitude modulation. So if my mirror is completely perfectly at 45 degrees, it radiates, kind of guides all of the sort of coupled power toward the second slit. So I have maximum reflected power. If my mirror is misaligned, then I'm like not all of the waves will see the aperture, the second aperture. So not the amount of reflected power is of course smaller. Like, and you can model that. Like here the equations show how you model that. So by changing the orientation of the mirror, I am changing the amplitude of the reflected signal, and that contains my data. Here are some simulation results to show with different MEMS mirror configuration. Here, for example, it's perfect. You can see that most of the energy is radiating or seeing the transmitted slip. Here, because it's sort of tilted a little bit, not like most of the energy will actually kind of go around the second slit, not being emitted. Okay, so this is our prototype and testing setup. So the transmitter and receiver is as before, an ultra-wideband transmitter and an ultra-wideband detector. This is our dual slit Leaky scatter. The MEMS mirror is inside, you cannot see it. What you're seeing here is the controller. Yeah. And these are my transmitting and receiving assets. So first thing we tested is the retro-directivity of the link. So we try different transmitting angles and we measure the power spectrum across different receiving angles. So ideally, if your transmitting angle is at 30 degrees, you're supposed to see maximum power at the receiver when it's located at 30 degrees, right? That means retro-directive. And you can see that matches to some, like it's aligned, well aligned with the expectation. Here, this plot shows exactly the transmitting angle versus max power reflection angle, and this should lie on y equal x, which is at least to some extent aligning with y equal x. Here we're sending the data, so we're sending how the amplitude is changing. This is at different frequencies, so different backscattering locations, and you see that the measured power pretty much matches the data flow 001, for example, that we had here. Interestingly, you can also scale this to multiple backscatters because they're operating at different frequencies. So you can have multiple backscatter nodes sending their data simultaneously to one local, like external transceiver. So I won't go to the details for the sake of time. Okay, so I covered the first 3 topics. I'll quickly touch our sort of wireless security efforts, but happy to take more questions on this. So a myth about terahertz is that terahertz is secure because it's directional. So omnidirectional transmission is more sort of vulnerable to eavesdropping because the eavesdropper can be anywhere and you're sending your information everywhere. It's now terahertz is directional, so you are more secure. Well, that's true and it's false. Even though your data transmission is directional, you have to do some beam training to find that directional angle before that, right? And that is quasi-omnidirectional. You try all the other all directions. So there is vulnerability in the control plane and the beam training files that people sometimes forget about. Also, we have to deal with new infrastructure right now that are meant to improve resilience. One of them is smart surfaces. I'll talk more about this in a second. So this new infrastructure is supposed to help you recover blockage faster, but they come with actually new vulnerabilities for wireless networks. And then last but not least, because your communication is directional, you need to know some information about the location, at least angular location of the receiver. So that raises sort of concerns about the privacy. If there are two users that are communicating to each other, they need to know their angle, but then that can help like an adversary localize basically a victim here. And that's the privacy. So what I will talk about quickly is just a new infrastructure to the smart surfaces part. So smart surfaces are an emerging sort of topic that help you reduce the blockage by covering the dead zones, by giving you non-specular reflected path that you can control. And these surfaces are typically passive, or if they have active components, it's a low-cost, scalable active component. So the idea is instead of deploying more access point, you can just deploy more of these scalable, low-cost surfaces to improve the performance of your wireless network. But that means that gives sort of an adversary in the network a benefit, because these things are very naive, scalable, low-cost architecture that can be easily controlled by an adversary. So one of the things that we studied in our ACM Hot Mobile paper is that what if an adversary controls on a smart surface? One possible attack is that it can now kind of control this control signal that is applied to this smart surface element and create a sideband and control that sideband. So it gets a copy of the signal no matter where Mallory here, your attacker, is located. The principle of the attack is very simple. It's based on a space-time coding. So the goal here is that you have a beam toward Bob, so you don't want to see a lot of drop in power at Bob, because otherwise Bob would detect the attack easily. But you also want to have a copy of the signal being transmitted to you at a slightly different frequency. So if you vary the control signals in time domain and have that in a periodic manner, you create a harmonics. If you impose delays in sort of inter-element, like that inter-element delays, you'll see that you can actually, based on the delay that you apply, you can steer that sideband toward Mallory's location. More interestingly, you can also control how much of the power goes to Bob, how much of the power goes to Mallory, because the impinging power on the surface is fixed, right? Surface is not sort of creating power by its own. So it's fixed, but the way you distribute this in a spectrum, in a space and in a spectrum, it's controllable. How? By basically choosing the duty cycle of these time varying control signal. I don't go to the details, but you can see that here, if like Mallory has a better channel or it's closer to the surface, you can reduce the power for Mallory and get a better power at Bob. So in sort of decrease the chance of getting caught. But if Mallory has a bad channel, you can kind of sacrifice Bob's SNR to get a successful attack. We, with collaboration with my colleague at Princeton, we actually designed the surface and implemented this and did the sort of the first round of experiments where we have an external transmitter, the millimeter wave surface. It's an 8-element surface at 60 gigahertz. We haven't done this at terahertz yet, but the principle should be similar. So it's kind of the same concept. External receiver is on the other side receiving this. We move the receiver around to get like the radiation pattern for main band and side. Here it's like some results showing that the main band, which is like the light green pattern, is fixed but the side band, which is our first harmonic here, can be steered independent. We also showed that like you can control how much loss you see in the main band compared to the side band. Cool. I think I am 4 or 5 minutes over my promised time, but I just want to acknowledge the contribution of my students at Swan Lab, all of my collaborators at Rice, Brown, Northeastern, Princeton, and also Intel. Also, I want to thank our sort of funding agencies and NSF, Intel, Microsoft, Air Force, and others. We have several PhD openings and postdoc openings. So if you're interested in this field of research, do not hesitate to send me an email. Thank you.
Excellent. Thank you so much, Yasemin. Please post your questions to the speaker on the chat. We do have one question. So, does contraction and expansion of the metal due to temperature affect the leakiness?
Yeah, so you're talking about, like, if I understand the question correctly, if temperature affects the efficiency of the leaky antenna or how much power you get out of it. No, it doesn't, because the sort of Maxwell equation, the boundary conditions that you see, this is not a function of temperature. So we tested in normal temperatures in the lab, in winter, summer, results are the same.
Go ahead. Yeah.
This is another excellent presentation, so much to digest. It's not easy to follow you in all details, but in general, I have a few questions. First of all, when you say leaky cable, usually is for indoor and long distances and in tunnels, things that you install in indoor buildings. But is it the same concept of waveguide for you, leaky cable antenna, or are two different things?
So, okay, so if you have a waveguide, depending on if it's a fast wave or it's a slow wave, it might stay inside the waveguide or it might leak out, right? Assuming you have an open state. Now, waveguides typically been used, as you said, to transfer a wave with low sort of attenuation from one point to the other, like in a circuit, for example, right? But the concept of leaky wave antenna has been out like since 1940. So yes, the physics of the problem is known, right? But what we're doing here is that, and we are the first to think about the application of this cool device in the context of communication and sensing and localization. And that part is new.
The other question, the access point at the physical level and even medium level, we talk about TDMA, CDMA, or so forth, or OFDM. In this case, in what kind of category you can put the access scheme?
Right. So here you can think about frequency division multiple access, maybe, because
FDMA. Yeah,
so you can serve different users at different frequencies, but it's also a space division multiple access, right? So it's a joint. I think there's no term for it. So it's a joint frequency division and a space division multiple access.
And the final question. Is this for only broadcast application or can be for mesh networking as well?
Yeah, so it can be. So what we're doing is we're introducing a new beam steering approach. The way you want to use it is like the control plane and MAC layer around it, whether it's point to point, whether it's mesh, whether it's broadcast. It's up to you, I guess. So it's going to be like the principle is going to be the same, but the applications or the network architecture can be anything.
And the other final one is this transmission for how long can be in higher frequency, like it's 80 gigahertz. Are you expecting with the beam forming to reach transmitted to receivers in long distances, or?
Yeah, so you're talking about the range, yeah.
Yes.
So here, like, we have an optical table in the lab, which is like 3-4 meters, and we can easily get from one side of the optical table to the other. But this is with minus 100 dBm of output power. So it is extremely low power. Now, if you just look into IEEE standard documents and like what is a typical output power, and you just like put that value and like write link budget, you can see that the link can be easily scaled to hundreds of meters. And in fact, like hundreds of meters of terahertz link has been demonstrated before, not with Leaky wave antennas, but with other sort of RF front, it has been demonstrated before. What we are losing with the waveguide is the coupling efficiency that we have, which is how much of the power leaks out of the waveguide. And it's about 90%. So we are losing 10% of the power just because we use the Leaky wave antenna. Everything else is...
Thanks, Nader. Yeah, thanks, Nader. So let's give Daniel, please go ahead.
Yes, excellent presentation. I just have one question on the retro-directive example that you gave. I was curious how you avoided or how you solved the full duplex communication problem. For example, if you're transmitting, you're piggybacking off of the transmission of the terahertz beam, but then it's coming right back at you. How do you receive the recipient's data?
That is a very good question. So right now, if you noticed in my sort of little picture, the transmitting and receiving slits are a few millimeter, like 1 centimeter maybe apart, right? And that helped us by focusing the transmitting and receiving slit get away with that. But we are working on another project where we use like carbon nanotubes to polarize the signal inside the waveguide. So then the polarization would be different, and we won't have that self-interference problem. But that is an ongoing project, so we'll see if that works.
Thank you very much.
So we have some questions on the chat. Question from Weeping. Are you using passive beamforming in the smart surfaces?
How are you using passive beamforming?
So how the beam pattern is formed in the smart surface angle, is it passive?
I see. So the surface that we have uses active like amplifiers, like LNAs, but there are like custom designs. So the chip is fabricated by a collaborator, so I'm not a circuits person. But we have active components, and we believe that in millimeter wave and terahertz, it makes sense to have active components, at least a few active components. Otherwise, the loss will be just too high that it doesn't make sense to have the smart surface anyway. But having that said, the principle of the attack that I just explained has nothing to do with whether it's a passive surface or an active surface. It just needs some controllability of the surface element, or like more specifically, the control signal that the bias signal that is getting applied to the surface elements. That's it.
Excellent. A question from Jazib. What additional considerations do you see in scaling up the lab prototypes for commercial applications?
Yeah, great question. So one of them is, of course, range. And we get this question a lot. So this will require a new sort of transmitter and receiver designs. And that is an active field of research, how to generate high output power transmitters in these high frequencies, and that's a hot field of research. The other sort of interesting aspects of this would be if you think about deploying this in practice, and I didn't have time to kind of skip through that rotation estimation part real quick, but if you think about deploying this in practice, you basically have to deal with the random orientation of this receiver, and then now your received power would be a function of that, right? So maybe we need another architecture that is cylindrical, or like it has like another geometry that deals with that type of orientation mismatch. And that is something that we haven't sort of investigated so far.
Awesome. And the last question, at least in the chat window, is for the range measurement, how much accuracy can be achieved, and what parameter decides the accuracy?
Great question again. So I don't remember the exact number. It's a few millimeter of resolution, but that totally depends on your bandwidth resolution in your sort of spectrum reading and measurements. So right now, because we have an ultra-wideband detector, our sampling rate gives us the sort of intersample of 1 gigahertz in frequency. So every 1 gigahertz, we have a new reading, right? So that's what limits us. And with that, we could get to, I guess, a few millimeter in terms of ranging resolution at the short distance of like less than 1 meter. But if you have a better receiver, because your bandwidth again maps to the accuracy, you can do much better.
And one more question, I think, this, in general, like, are motion sensors like gyroscopes and accelerometers feasible for beam tracking at the terahertz?
Okay, so if you're thinking about commercial gyroscope and accelerometer as they are right now, no. But if you're thinking about, okay, if we have next generation or like more advanced sensors, motion sensors, then probably, I don't know what would be the case 10 years from now. The reason they're not helpful is that the level of resolution is just certainly not match the requirement that we have. Also, they have problem with drifting and all sorts of errors that we cannot tolerate at this such high frequency sensitive scenario.
Perfect. We are at the top of the hour. Thank you so much. This has been like really interesting and like thought-provoking talk. Thank you for joining us, and thanks everybody for joining us for this talk. Stay tuned for the next big thing talk, and we'll stay in touch, Yasemin. Thank you so much.
Thank you. Take care.